you said advanced? What do you remember the class number? You could not take it, but then you could not take it. There's always that's it's too late to get outside.
Okay, test. All right, let's get started. So today, reinforcement learning is something a bit too different from supervised and unsupervised learning we have seen so far. And today, so I'm gonna just do introduction to all the elements that we need, like what is an environment, state space, action space, policy, and all those kind of things. And next time, we're gonna see one or two algorithms to solve the reinforcement learning problem. I try to gamify the lectures, sort of too many colors compared to the usual slides. So let's see. Yeah, we'll start with some examples. Then we're gonna go through the reinforcement learning components using a toy example, and then we're gonna do the formal definition using math. And so far, or like in these two lectures, we're just gonna concentrate on everything is deterministic, so you don't have to worry about too much probabilities. Okay. So when do we use reinforcement learning? Some examples is that if you have like a robot arm and you're not good at physics, or just physics is too complicated, and you want to learn the optimal dynamics of the arm to reach a certain, to achieve a certain movement, and you don't want to do all the equations, so you can just run different experiments and see which one is the smoothest. And so in this case, you're gonna, the score here is that the smoother the movement, the better the better the algorithm does. And you want to basically reinforce that behavior. Whenever the movement is smooth, whenever like the acceleration is bounded by a certain threshold, then your target is achieved. The second one, and this is usually done in simulations, is that you want to train like a robot to move a certain object from one zone to the other. Usually we do this in simulations because in practice, you would need thousands and thousands of trials and errors. You might break the robot. It may take days or even weeks. So usually we start with simulations before we transpose that to real robots. Or more recently, the AlphaGo, if you have heard about it, there was this myth that computers could not beat like human players in the Go game until Google came with the AlphaGo algorithm, which is based on reinforcement learning. And since then, there have been many iterations. So now you have all these machine learning scientists, each one trying to improve the algorithm, and they have their own competitions online, who has the better algorithm. And all of these environments, let's say, they have, there's one way that we can abstract all these three environments. And that's what we're going to see in the next section. Okay, this is just to give you a reference. We have three types of learning in machine learning: supervised, unsupervised, and reinforcement learning. Some people would agree that self-supervised is part of unsupervised, but that's another discussion. Okay, So in supervised, you're given a data set that consists of the feature vectors and their labels. You are supposed to produce some hypothesis, H, that will try to replicate or imitate the relationship between X's and Y's. And then you have a performance measure, which is the loss function. You can look at it as the accuracy, for example. Okay? So your algorithm is evaluated based on that loss function. In unsupervised, it's almost the same. And in this case, you have data and you want to learn some latent representation of those features. You can look at dimensionality reduction, or most recently in Homework 4, we're doing Gaussian mixture models. And the performance in the Gaussian mixture models was the log likelihood. So a good mapping or a good representation will have a maximal, a better log likelihood. In dimensionality reduction, a good representation in that case will be the one that will allow you to reconstruct the input as accurate as possible. In reinforcement learning is different. We're not given the data, but we are given a certain environment that we are interacting with, okay? And while we are interacting with the environment, we are gathering a certain data set. You can look at it as 3 tuples. We're gonna see later what they mean. And the reward is not, or basically the performance is not evaluated immediately, because at each interaction you're taking decisions and you are evaluated based on the sequence of decisions, okay? You don't get the reward immediately telling you that whatever you learned, the decision function pi that you learned here, whether it's better than previous ones or not, okay? So we have basically to construct a different logic for evaluation, for training, and for modeling as well, okay? All right, so this is our grid or toy environment that we are going to play with today. It's very simple. It's a 6x4 grid. We have the green square, that's our target. If we reach that, we get a +1 reward. And blue one, we get a -1. And the red squares, those are walls, so we cannot cross, okay? So in this case, the agent starting at position 0, 1, that's our initial position, will have to find a way to reach +1, okay? Usually in reinforcement learning, we don't try to tell the agent, okay, you go up 2 times and then right 2 times. We have to design a certain algorithm where we just give the agent the access to the environment, interact with it, and it has to learn the target or the optimal path by itself. We're not trying to do like algorithms with A* or some depth first search or something like that. That's another class. We're not doing that, okay? So that's basically what we said, is that the agent interacts with the environment. When it moves to each square, we will reward it on the transition. I have to mention here that we are speaking mathematically. Reward is not always something positive. It's like just in math, you can say, I gave you -$1, so it's the same here. You can have a reward of -1. It basically means a penalty of 1, okay? But here, we just reward. It can be plus or minus. Okay, so the agent at each position will try to take a decision, go up. Once it takes a decision, it's going to transition to another state. And that's basically what we call the state space. In this case, we have a state space that contains 6x4, which has 24 elements. Not all these states are accessible. It means that we have 3 states here. The square ones are not accessible. We cannot access, okay? But that's not an issue. We just interact with the environment. If we change the position, that's good. If we don't, it means that we hit a wall, okay? If we get a reward +1, it means we reach the target, and get -1, then we reach the pit. That's basically what we should avoid. In this example here, and most of the examples that we see, we assume that the state space is finite, which is not always the case. You can imagine you have a plant watering robot, and You want, for example, in this case, the state space would be like the humidity in the soil, the temperature, and other measures. In this case, the values can be continuous, so you can get infinite possible values of the state space. Okay, so you can think of very simple examples where the state space is infinite. Okay, we note S0 just the initial state. In this case, the initial state is 0, 1, and we're going to see how important that is. As I said before, the actions that we can take at each position is like, in this case, 4. And the same as the states, it can be infinite, it can be finite. We can take four actions at the same time. You're going to say, well, I can't go left, but we don't care. You can decide, well, I'm going to go left, but I cannot. So it means that the next state is just going to be your current state. The state does not change, okay? So to make it simple, you can take any action at any position, but it doesn't mean that going to the right means that you're going to always move to the right square. Any questions so far? Very clear, okay. All right, so this is the transition. So the transition probabilities or the transition dynamics, these are inherent to the environment. We assume that we do not know what the transitions are. So this is what we call model-free reinforcement learning. It means that we have no prior knowledge about the environment. Okay, it's not like chess. In chess, it will not be model-free because we know the rules of chess. We know the positive movements. We know how the different dynamics. But usually, if the environment is just black box, then you don't know what the transition probabilities is. So what do I mean by transition probabilities? It just means that if I'm a certain state and I take a certain action, what is the distribution over the state space? It means what are the possible states that I can move to if I take an action. So in this example, in my initial position, 0, 1, if I go to the left, then I'll just stay at the left. Yeah, I mean, in my position. So in this case, probability that I move to 0, 1, starting from 0, 1 and going to the left is 1, okay? And all other positions will have, all other states will have probability 0, okay? Similarly, so basically what I said is all my probability goes to 0, 1, means I'm just going to stay. It means that probability of 0, 2, starting from 0, 1 and going left is going to be 0. Okay. So here, a very simple question. What is the position, what is the state that I should put here to have probability 1? Starting from 0, 1, going up. 0, 2, okay. That was easy. We will call a replay or a rollout is that basically you are running or you're playing the game or you're exploring the environment until the episodes finish. And in this case, the episode finishes when we reach either +1 or -1. If you reach +1 or -1, you're basically resetting the environment and you're going back to start from the position is 0. It does not mean that we have a finite horizon, because I can basically take another path where I'll just keep turning around the first red square, and that will go infinitely, okay? And in this case, for each action, as I said before, for each action we take, we're going to transition from one state to the other that is determined by the transition probabilities. And for each transition, I'm going to get a reward, okay? So the reward function is something inherent to the environment. It can be deterministic. It can be random. Like you can imagine playing some lottery and you're taking decisions, but sometimes you win, sometimes you don't. In the example, in this case, it's deterministic because we know if you reach a 5-3, you're going to get +1 with probability 1. If you go to 5-2, you're going to get -1 with probability with probability 1. So everything there is certain. And as I said before, the goal here is to maximize the objective. In this case, we want to find what's the optimal action to take at each state, okay? And optimal means that the one that will allow us to reach +1, okay? While avoiding -1. This class on reinforcement learning, we won't cover single state spaces, and that's called ARM Bandit, and that's a different problem. If you want to go a little bit hardcore on math, you can try ARM Bandit. So we assume that we have at least 2 states, and that we can move from one to the other. It doesn't mean that, well, you can have 2, but you can only operate in one, so it means just a single state space, basically. But in this case, we can imagine that we have at least 2, and we can move from one to the other based on the actions that we take. All right, so what we are going to do is learn this function that we're going to call pi, so that at each state, it's going to return an action, okay? And the goal here is to find the optimal one. You can look at it as the hypothesis that you are giving it features and you want to return a certain class, okay? It's the same thing, but here is a different type of data. This formula is for deterministic. Usually in reinforcement learning, you can see the non-deterministic one, which means that for each state an action, you have to get a distribution over the state space. Okay? So previously we saw that, for example, if I'm at position 1, then with probability 1, I'm going to take action up. Okay? So you can map the state directly to the action. In other cases where the environment is random, everything is random, if you use a deterministic one, let's say you're playing a game and you increase the difficulty, if the game knows that you always go up, they can penalize you for going up. So in that case, this is related to game theory, you want to have a random policy so that the game would never be able to guess your action. Okay, so in that case, you want to go random. But in our example here, in the homework and the assignments and everything, we assume that the environment is just doing its job. It doesn't care about how well you do. All right, so this is an example of a policy. Okay, so at each position here, it's just going to tell me where to go. And you can see that all of these actions, it doesn't matter which state I'm at, it's going to lead me to the target in the shortest distance possible. Okay? One thing to note here is that if I start from 0, 1, I can go up and then all the way to the right, or I can also go to the right, up, and then to the right. And you can check that both of them have the same length, okay? So the shortest path to the target or the optimal policy is not unique. This is something to keep in mind. The optimal policy is not unique, but there's something unique that we're gonna see what it is. So as I mentioned before, we are always looking for something optimal. The policy, optimal policy, what is optimal policy is something that will allow us to take the optimal action at each state, but what does mean optimal, okay? And the intuition here is that the optimality is just how many rewards that we get, okay? The sum of rewards that we get while exploring the environment. Okay, so in this case you say, well, my reward is 1, I'm going up 2 steps and then right. I'm reaching it in 7 decisions. 1, 2, 3, 4, 5, 6, 7. Yeah, I have to take 7 actions to reach the target. Okay? And what we call a replay or a rollout is just the sequence that we get. We start from S0, we take action A0, and then we are given a reward R0. I forgot to plus there. Okay? So if you remember the data that we are gathering in reinforcement learning, we said we're going to have, instead of X and Y, you're going to have tuples of S, A, and R. So S is the state, A is the action, and R is the reward. So we start in as S0, we take action A0, and we get in the reward. And the cycle repeats. Now we move to S1, we take in another action A1, and we get in a reward A1, R1, okay? Yeah, so we said 7 steps, but we're starting from 0. So S6 will be this state here, and we just have to take the action right, and then we're gonna get R6 equal 1, okay? So the accumulated rewards, just the sum of the rewards that we get through this path, and you can easily tell that this sum is 1. The problem here is that we can have different paths that will give us reward 1. But we can see that policy 1 is not really is not better than policy 2 because it's taking more steps, okay? But we're still getting reward 1. So the trick here is something that, okay, so this is 8 steps. The other one, we're gonna just have 6 steps, and both of them achieve the same reward. So the trick here is that we're gonna add what we call a discount, okay? So it means the later you get the reward, the less the value or the objective value that you are going to get, okay? And in this case, it's no longer the sum of the reward, it's the sum of the reward multiplied by a factor that we call discount rate, gamma, to the power of the number of steps that you take to reach that reward. So if you go back to our example, let's use a discount rate of 1/2, okay? So what would be the objective value for policy 1 and policy 2? If we use gamma equals 1/2, like 0.5. Knowing that in policy 1 we take 8 steps, and policy 2 we take 6 steps.
What do we subtracting 4 and 3 from our final reward?
What's that?
What do we be subtracting 4 when we take 8 steps?
Why 4?
8 divided by 2 is 4.
I said gamma is equals to 1/2. If we take gamma equals 1/2, we have seen the sequence of the rewards. Okay, let's go back to the sequence of the rewards. Okay, so here we just sum the rewards. In the discounted version, we're not doing just that. We do like R0 multiplied by gamma to the power of 0, so RT to the power of RT multiplied by gamma to the power of t. So in this case, if we add that gamma factor, what's the total sum? Okay, you don't have to compute it. You can just say, well, yeah, doing gamma over 2, so you just sum in gamma to the 0 multiplied by R0 plus gamma 1, R1, and then you go all the way to gamma 8, R8. We know all of these are 0, so we just disappear. So in the end, we're going to end up with 2 to the minus 8. Okay? For policy 2, we have 6 steps. So in this case, the accumulated reward is 2 to minus 6. So in this case, when we use the discount rate, we can see that policy 2 is better than policy 1. Okay? This is just to give you an intuition why we discount the rewards. The other one will come when we're going to look at the algorithms, because we're going to see that there's some, our optimality bounds are going to be a function of 1/1 minus gamma. And we definitely don't want gamma to be equal 1. Okay? Because if gamma equals 1, then we just, if gamma equals 1, then this just becomes the sum of RT. So we're going back to the example we had before. Okay? All right, so we have gone through state space, action space, transition probabilities, rewards, policy. This is everything we need to start doing the real reinforcement learning. And in this case, we call it Markov decision process. It's Markov because of the transition probabilities P. If you have studied Markov processes, you would know why it's called Markov. Okay. But in this case, we just assume that we have a tuple of all these elements. S the state space, A the action space, R is the reward function that will reward us for transitioning from ST to ST plus 1, okay? And the transition probability will tell us that if we are at ST and we take action AT, then what's the next state, okay? And this is a simple abstraction of all reinforcement learning problems. You can imagine the agent here is at state ST, we take the action AT, we transition to ST plus 1, and we are given the reward RT. So what we do here at each step, we are gathering these three elements to form our tuples ST, AT, RT. Okay? And that's what you're going to call a rollout. Okay? And we can either play until the game is reset or play and set for certain steps. Okay? Depending on the environment. And the objective is to learn autonomously through trial and error the policy P from S action to distribution over the action space that will maximize the expected accumulated rewards. Okay? So I'm adding expectation here just to follow the formal definitions because the environment can be random, the rewards can be random, and the policy can be random. Okay? But if you want, where everything is deterministic, it's just the sum over t from 0 to infinity of gamma t r st, and here's going to be pi of st. Everything is deterministic. You can have different types of writing, but this is the formal way. Yeah, we already talked about this. We are taking, the actions are taken following the policy pi, and the action sequence will determine which state you are going to get, okay? So when the sum is actually tricky because here we're doing the expectation with regard to pi, and the question here, we don't see pi here, okay? But the interaction of pi is that it's going to control st plus 1 because st plus 1 is basically determined by the transition probability, and knowing that I am at st and I take the action based on st. Okay, so P here is actually involved in st plus 1. It controls the transitions in a way. So expectation with respect to the policy, because the sequence depends on the policy that we have, that we are going to use. Okay. And since we have expectation here, we can do some conditional probabilities to break down the accumulated rewards. So in this case, you say, well, I'm starting from S0. In our environment, it was 0, 1. Okay? But you can say, well, I don't want to look at the reward starting from S1, from 0, 1. I want to look at the accumulated reward starting from any state. Okay? And that's what we're going to call the value function. So instead of starting from F0, I'm going to determine what's the initial state to start from. All right? So we said that if we start from 0, 1, we get V pi for our policy that we had before. We called it P2, policy 2. We said that it's going to be 2 to minus 6. Okay? If we start from one state above, from 0, 2, then we can reach the goal in 5 steps. In this case, it's going to be V of 0, 2 is going to be 2 to minus 5. Okay? And then from that position, you can do the same example. So if you reach V of 4, 3. Okay, let's do this. V of 4, 3, let me go back to the environment. What's going to be the value function at state 4, 3? Let Let me go back to the value function. If we start from 4, 3, what's the expected accumulated rewards?
Yeah.
What's that?
Yeah.
Nope. Very close. One step down. So it means that S0 is 4, 3. I take action A0, which is right. And what would be R0? It's going to be +1. So in this case, the sum would be gamma to the power of 0 R0. Makes sense? So gamma to 0 is just 1. So it's going to be 1. Okay? Yeah, actually, I kind of misled you here because if we start from 0, 1, we're actually taking 7 steps, but we get to the -6. If we start from 0, 2, we're actually taking 6 steps, so we're going to get to -5. If we start from 4, 3, we take 1 step, so it's going to be 2 to 0, which is 1. The sum here starts from 0, okay? It doesn't start from 1. All right, so we can just go and do this kind of manually to find all the possible. We can compute the value function at all positions. We already provided here for 3. So once we go 1 step away, we're going to have gamma 2. Okay, I'll let you complete the rest. What do you think? Does it make sense or questions? Should I go back and explain it again? We have some time. Okay? So here's going to be gamma 3, gamma 3, gamma 4, gamma 4. And you can basically go and do the same thing, right? Gamma 5, gamma 5, gamma 5. Sorry, -2, -1. Oh, sorry, no, it's good. Okay, so because gamma is 1 over 2, all right? So gamma 2 is 1 over 2, 2, 2, so it's 2 minus 1, it's good. So here's gamma 6, gamma 6, gamma 6. So here's gamma 7 and gamma 7. So we had a mistake before, okay? 1, 2. This is, we can't access this. This is a wall. So those states, we cannot access them.
1, sorry.
2, 1.
This is right next to a 3.
Yeah. This is. So 2, 3, yep. Sorry.
It's interesting to see how you teach this, because we went over Markov models in our AI class, but we went at it from a different perspective.
Yeah. I mean, I done reinforcement learning for like 2 years. And if I show you the math, you just equations, what does it mean, value function. So I want to give you intuition what they actually mean.
I appreciate it.
So, because if you look at equations, they don't talk. You have to give examples, yeah.
So are we working back from the reward stage here and iterating?
Yes, and that's actually what's going to happen in the algorithms when we solve them. Because when you are starting from states, from the initial state, you're just exploring the environment, you're getting no rewards. Once you reach the reward, you say, okay, I was in this state, and I took the right position, the right action, and I got 1. So you're going to, okay, now I'm going to put 1 here. Now you do the same again. You just walk, and then you say, wait a second, when I reach this position, I took 1 step and I reached 1. So now I'm going to multiply by gamma. So what's actually happens in the algorithms is exactly what we did here. You're going to reach the goal, save it. In the next iteration, you're going to, so the first iteration, you're going to populate this one. the second iteration, you're going to populate the neighbors of that one and vice versa. So once you fill all the cells, you're going to say, okay, now if I learn the value function, what is the optimal policy? The optimal policy is if I am at this position, I'm going to think what's the neighbors that I have that have a value function larger than mine. Okay? So if I am in 0, 1, I'm going to look at my neighbors. Keep in mind that gamma is less than 1. So the higher the power, the smaller it is. Okay? So I get gamma 5 and gamma 5. So I have the choice between going either up or right. Once I am here, then I'm going to look at my neighbors. I'm going to look at what's the neighbor that has the highest value. You see? So I'm just keep following those traces. Example is like the ants. So when the ants find food, they just screech pheromone. The closer you get to the food, the stronger the pheromone. Something like that, yeah.
If we had another reward state, like at 5, 0, would you then, how would you recommend?
At 5, 0? Yeah, so we're going to see that. Yeah. We're going to see that, in this case, example is very simple, but when you have multiple states that one give you like 0.5, other 1, 2, 3, well, you're going to see that, we're going to look at that next class. You can learn it in the same way. The only thing that you get is that you have a guarantee that you are going to converge to an optimal value function. Okay? So when do we use the value function? We use the value function where the action space is finite. It means that I know I can take 4 actions at each state. I'm going to take 4 actions, and I'm going to say, well, if I take this action, I'm going to move to the other state, and I can evaluate the value function. Problem is when you have an infinite number of actions, it would be difficult to use the value function, the state value function, and that's where we use something else called the state action value function. Okay? So in V, we say we're going to start from this position. We're going to determine the position and then follow the policy. In Q, we add another initial condition, which is the action. Okay? Oh, actually, I don't have this because I have another example for it. Okay. So in Q, I take the same expectation, but this time I'm going to say, okay, starting from S0, and I'm going to go down. Now, what's the expected reward? That's basically the question that we get. Okay? So in this case, it's going to be R, S0, S1. Okay? And S1 here is actually just given by P at S0. I'm going to take action A0. Okay? Plus gamma. Now it's going to be S1. And after that, I'm just going to follow the policy S1. Okay? Yeah, this is basically there's a sum here. Yeah. This is fixed. This is deterministic. So this goes out from the expectation basically, and then you get an expectation here. Okay. So here we're just conditioning on this. It means that the first term just is going to leave the expectation because it's no longer random. It's determined by the conditioning. Okay. And we can see that there's some logical thing here, because if we remove this, if we factor by gamma, this is basically Q of S1. Sorry, V of S1. Does it make sense? We're going to prove it later. Don't worry. We're going to go back. I'm leaving that for next class, so we can go through the definitions. You have like 48 hours to get familiar with all these notions, because on Wednesday, I'm not going to slow down on these things. All right, so I'm just zooming here, because we're not going to do it for all the state space, because at each state, we have 4 actions, and I'm not going to do like 4 by 24. But let's look at the example here, okay? So let's say this is my state here, and I want to compute, let's call this S, which is 4, 3, okay? And I will compute what's my expected reward if I go down, and if I go left, up, down, right. Okay, let's start with the first one. If I am at this position and I go left, then I end up here. Okay? If I end up here, what reward do I get? I get 0. Okay? Then I'm going to say, okay, now I'm going to do gamma plus gamma multiplied by, and if I follow the optimal policy, then basically I'm going to get the reward that I get here, which is gamma, basically V of 3, 3. And we saw before that this is gamma. So if I go to the left, I'm just slowing myself down for 1 step, okay? Which is equivalent to taking 2 steps. Let's do it this way. If I am in this position and I say I'm going to the left, then I end up in this position, okay? So now I'm taking 1 step, 2 steps, 3 steps, which is equivalent to starting here. Because here I'm taking 1 step, 2 steps, 3 steps. Okay, so if I am at 4, 3 and I go to the left, I'm just slowing down myself for 1 step. Okay, so in this case, the QS left is going to be gamma squared. Okay, what about the other ones? Mm-hmm.
So if we have a positive gamma, essentially,
It's always positive.
wouldn't it be more optimal to run that out for all it's worth to get that maximum 1? Because obviously, if you add up all of the numbers between 1 and 2, you get another 1. So famous infinite mathematicians in a bar, you get 2 beers, right? So wouldn't we want to get that extra 1 by running around in circles for as long as possible?
I see what you're saying, but you are assuming that we are getting 1 for each step.
But we're getting
Yeah, but here, if we're getting 1, we get reset to the initial state. So you cannot just be hitting 1 plus 1 plus 1 plus 1. Once you reach 1, you get reset to the initial state.
Well, then wouldn't you be counting up your reward at that previous state? It would still be better to go back and forth.
What's back and forth? Because if you go back and forth, you're just getting zeros.
Aren't you adding gamma?
Yeah, but gamma multiplied by the reward. Okay, so keep in mind that in definition, we always gamma multiplied by the reward. If we reward 0, then you're just adding zeros. Yeah. Okay, so up and down is the same. You're just going to slow down yourself for 1 step. But then you have to the right side, you are getting plus 1. Okay. And this is where I said we want Q when the action space is unknown. Okay. Because the Q will give you the expected accumulated reward for each action. Okay. So in this case, we know that we're going to take the right action because it's going to give us 1, which is larger than gamma squared.
Why is it gamma squared for opposite? Don't you like just end up at the same square and you go once over so it would be gamma?
Yeah. So if you go up, you're starting from this position. Okay. You go up. It means that you're starting from S, call this S, 3, 4. You go up. You're going to stay in 3, 4. And then you're going to go right, and you're going to get plus 1. So here, if for this action, what do you get? You get gamma to the power of 0 multiplied by 0 because we're getting no reward. Plus, now you're going to get gamma of, what is it? So now you're going to the start position. Yeah, So if you go up, it's going to be gamma. Yeah, this is just gamma. Yep. Yeah, because in the other ones, you're pushing yourself one step away. So for up, it's going to be gamma. It's not gamma squared, thanks. Okay. But it's still lower than 1, so it means that the optimal action is still 1, to going to the right. Okay? Yep.
And then is the value of this function and the reason you use this if you have, like, maybe not a friendly finite amount of actions. Instead of doing it for every single point, you can just kind of have, okay, point I am right now, what's the value of everything now?
Yeah. But we're gonna have Q value for each state, okay? So for each state, you're gonna compute here as well. I'm just too lazy to do it and it takes too much time. Yeah. The advantages of Q is that you can guess the action directly, okay? Which is different from V. From V, you are looking at the neighbors, but you have to figure out what's the action that you're going to take, right? If we go back to V, for example, we said this is gamma 6, this is gamma 5, gamma 5. You're going to say, well, I have a neighbor here that will have a better expected accumulated reward, but I have to guess how can I move to these, okay? That's the problem. If you don't know how to move to those states, then you have to figure out what's the action that I have to take to move from 0, 1 to 1, 1, or from 0, 1 to 0, 2. A Q, on the other hand, you can get the action directly, okay? Because we store in the accumulated reward for each pair state action, okay? And I'm gonna stop here. And I want you to look at these formulas. We're gonna we're gonna just skim through them next time. And these are called Bellman equations, okay? And why do we need these, or why do we use these? Well, we want pi that will maximize this value. So if we do pi equals argmax of q pi of SA, okay, we have only this term depends on pi. So when we apply the argmax, we're just going to have Rs, S, which is the pair of states, plus gamma argmax of V pi of S. So here, basically what I'm going to show is that the policy that maximizes the accumulated rewards is the only one, also the one that maximizes the Q function, which is the state action function, and then the state value function. Okay. We have seen that the optimal policy is not unique, but the optimal Q and the optimal V are unique. Makes sense? And if we learn the Q, let's say I get the optimal Q that I'm going to call Q star. Okay, then the optimal policy V pi is just the argmax with respect to the action of Q S. Okay, so this here it's going to be pi of S. So if I learn Q, I'm basically learning the optimal pi, one optimal pi. Because as we've seen before, we had gamma 5 at 2 locations. We had gamma 5 and we have gamma 5. So even though the Q is optimal, we can have multiple policies that will give us the same accumulated rewards. This is more formally using the non-deterministic formula. Sorry, and then we're going to see next time how to learn the optimal Q or the optimal V and get the optimal policy from those. Okay, I have 2 minutes left. Homework 4 already started. I'm not going to hold office hour today. I'm going to hold 2 office hours on Thursday because I'm busy with preparing the slides. And homework 5 is going to be the last normal homework where we'll be required to do some reinforcement learning, We're going to add probably some naive Bayes. We have to decide that. But I'm going to try to make it a bit chill. And I'm going to post a poll today for homework 6. Homework 6 is going to be a machine learning competition. So it's basically like Kaggle competition, if you're familiar with it. You're going to have a data set, and that's where you're going to do deep learning. So deep learning is not going to be part of the assignment. It's going to be basically, you're going to try to use PyTorch or TensorFlow. And we're going to post a poll to just see what you are interested in, like object detection, segmentation, forecast, whatever you like. Last time we had a ROC data set that has like 20,000 pictures, and they had to classify them into 50 categories. And they used Keras TensorFlow. If you like PyTorch, we can use PyTorch. It's up to you. And yeah, it's different. Last time we made them implement deep learning from scratch using NumPy. Yeah, I mean, yeah, I don't think we're going to do it this time. But if you want, I can publish the homework. I mean the problem, and provide the solutions later if you want to work on it. For Friday, we're going to do a bit of SVM because I'm sure you're going to be stuck with the SVM problem. So I'm just going to explain the logic there and what's going to happen, and it's going to count towards your participation because we noticed that we don't have a participation assignment. So we're just going to do the same style as homework 0. I'm going to give you some solutions to some questions, and for the others, you have to do them yourself and submit them. Okay? Any questions?